Mic check, 1 2 1 2 1 2. Good evening, good evening, good evening everyone. It is Wednesday evening, it is 8:30 and that can mean only one thing. It is physics time, and this evening we are in the Year 11 Tidy Up section. You've got your exam next week if you're a triple award student, and tonight we're going to go through just a couple of little bits and bobs that just need clearing up and made certain. Okay, so what we're going to take a look at tonight is we're going to take a look at acceleration and retardation, the deceleration side of that. The CS spec refers to it as retardation, so we will use that terminology. We will look at some 6-mark questions. We'll have a quick flick through the specification, maybe make a couple of flowcharts on good ways to answer a few of these questions. We'll look at nuclear, we'll maybe take a look at some of the energy resources types and so forth, and then leave a little bit of time at the end, hopefully, for any questions that come up in chat. Now I'm hoping that you're at the stage now where questions should be reasonably few and far between, but get involved, pop chat in the chat stream at the side, and we'll get to your questions definitely as we go. Alright, so starting with acceleration. So we have a variety of ways in which we can measure acceleration. Okay, a few equations that we need. Okay, so first of all, we can have acceleration equals change in velocity divided by the time it takes. And I'll do a proper fraction here as opposed to doing a slash. Divided by the time taken. Now, the word velocity there can be changed to speed, provided you're going in the same direction all the time, and acceleration here can also be called rate of change of speed. Okay, acceleration technically is the vector quantity that when you're looking at scalars, so when it's changing speed, is technically called the rate of change of speed. But they are essentially the same thing, unless you're considering direction. If you're not considering direction, you're just looking at a number, they are exactly the same thing. This breaks down into A equals V take U over T. So V take away U divided by T, all divided by T. So all over T. Just like that. Okay, V is your final speed, U is your initial speed, and T is the time taken. Once again, there are a couple of little tricks and turns that can be done in exams to just really separate those who know their stuff to those who like sat up all night and ground it into their brain without ever understanding it. And that's the beauty of physics exams, that we can really quite quickly discern between the learning people, you know, the people who like history and things like that, where you just learn it off. That's harsh on history, but you know, not entirely inaccurate, versus the people who really understand what's happening. And this is one of the places you can do that. So if I was an examiner, I'd maybe say an object slows down by 30 meters per second in a time of 5 seconds, and you should recognize then that that is the change in speed on the top here. That is V take away U. Right, so that's one way you can do it. You can also do the average acceleration, or sorry, the average speed, apologies, the average speed one, and that looks a little bit like this, which is a nice way to pop this in as well, that you can mess with people. That if you give them V, you give them U, and you give them a bit of time, but you ask them for the average speed, what you want here is V plus U divided by 2. Now, not necessarily related to acceleration here, but since it looks so similar to the equation above there, it's worth mentioning at this point as well. So we'll just highlight that and send that backwards so that it's highlighting. Okay, again, like I said, this is not an acceleration equation, but it does look an awful lot like this. This is just the average of two numbers. My first number here, my last number here, divided by 2. The average of any two numbers, add them together, divide by the number that there are. Okay, then finally, not finally, but we want to take a look at the other method of getting acceleration, which is using F equals ma, rearranged to A equals F over m. And really the first thing that you have to understand about this is when to use them. And this comes down to good exam technique. That if you get a question that has lots of numbers in it, it's the right idea, the only idea, the best idea of how to travel through that is, as you encounter these numbers, write them down and write down what their symbol is down the side of the page, so that you can then jog your brain as to which equation you want. So let's take a little example of that. Let's grab this question here. So let's say a car is traveling at 40 meters per second pretty quick, and has a resultant force of 3,000 newtons acting on it. It has a mass of 1,750 kilograms. What is its acceleration? Okay, so this looks like a pretty interesting question to have a look at. We've got lots of numbers going on here, and we want to find out, right, what's really happening here. So we've got a speed here, we've got a force here, we've got a mass here, and we're looking for an acceleration. Now the best way to approach this is to go, right, well, what have I been given? A car is traveling at 40 meters per second. So it's kind of its current speed. So we'll call that V equals 40. It's probably V. It has a resultant force of 3,000, so that's F equals 3,000. And it's in newtons, so we're happy with that. And it has a mass of 1,750, 1750, and that's in kilograms, so we're happy with that. And we're being asked to find A. And suddenly this becomes a really straightforward question, because you look at it and you go, right, I've got F, I've got M, I've got V, and I want to find A. And you really quite quickly make the connection to go, all right, this is A, F, and M here. That's this one. So we pop the numbers in here. We get A equals F divided by M. I'm not going to do a full fraction here because it's a pain to draw. So A equals 3,000 divided by 1750. So A equals, reach for the calculator, you go 3,000 divided by 1750, grab that, and we get 1.71 to 2 decimal places. And because all my units have been correct, this will have to be in meters per second squared. Okay, so that's just a general exam technique thing. Formula, working, answer, unit, up to 4 marks. And the 40 here was a red herring. It wasn't needed at this stage. Now it may be needed in different in the next part of the questions, because I could say maybe what was its speed 0.4 seconds ago, and then I would have V, I would have A, I would have T, and then I could use A equals V minus U over T to find T. And then let's just do that question just for the sake of running it through. So what was its speed, or its velocity? Let's do 0.5. 0.5, yeah, 0.5 seconds. 2 seconds ago. What an actual difference. Okay, so 2 seconds ago, so we definitely have V equals 40, because we're looking to find what was its initial speed. That was its speed in the past. Okay, so we're looking to find U. We have V. We know we want V, U. This is a question about acceleration, and we've just worked that out, so that becomes 1.71 in there, and we were told that T equals 2. Alright, so this is the equation that we're after. We also still have M equals 1750, and we have F equals 3,000. So we have all the information that we have at our hands now for this question. So here I go. Oh, apologies for the phone there, folks. Normally I have that in silent. Right, so our equation A equals, and we will need to write this as a proper equation. So A equals V, take away U, and then we want to divide that all by T. So pop that in, divided by T. Okay, so we've got a mark on the board for not doing anything yet. Now, a bit of rearrangement to do here. Now we can rearrange beforehand. I don't like doing that in these situations. I'm much more a fan of popping the numbers in and then working with numbers. Most people are better at working with numbers in equations than they are at working with letters. And since we've got all but one of the numbers, this makes sense. So this is 40, take away U, and then divided by T, which is 2. Okay, so first things first, we don't like that divided by 2. That's messing us up, because if this was just 40 take away U, it'd be easy. So we're going to multiply both sides of our equation by 2. So again, grab our calculator. I've got the answer left in from earlier, so we won't need a rounding thing. So we get 3.42, which is 2 times 1.71, equals 40 take away U. Now we've got a minus U here, but we're not going to worry too much about that. We want rid of the 40. So we're going to subtract 40 from both sides, because we've got plus 40 here. So take away 40, and that's going to give me negative 36.57 according to my calculator, 58 if you have done the rounding, equals minus U. Well, if minus 36.58 equals minus U, then U has to equal 36.58. If you're not happy with that, what I did there was multiply both sides by -1, which gets rid of the minuses on both sides. Okay, and that's our final answer. And this type of question, you'd probably be looking at 4 marks for that. Okay, now the real problem becomes what if we throw an object up in the air? And this was a question I got asked in class today. You know, really, what are we talking about in terms of deceleration going on here? So I've got an object on the ground and I throw it up into the air. Right, now at the moment it's launched, there's a force acting on it, but as soon as it leaves whatever it is that's fired up in the air, like a cannon or a hand or a tennis racket or whatever it is, the only force acting on it downwards is the weight. Okay, W downwards, and there's no force acting upwards. It's just going because of the fact that it was hit. It's going to stop, it's going to come back down. The problem is here, let's say we have a situation that we get told it was launched upwards from rest or from the ground at a speed of, let's say, 25 meters per second. Okay, and that's all we've been given, and we're asked how long before it stops. So how long before it stops? That'll be when it's at its maximum height. From the people that were at energy last week, because when it stops, its kinetic energy becomes 0, so it will be at maximum potential energy. So at its absolute maximum height, it's going to have no speed. But the problem is that we're looking at this going, right, how long before it stops? So we want a time. That's a definite question. We know at the end v is going to be 0, and that's an important thing, that we haven't got a number here, but it stops means its final speed is 0. We know that its initial speed is equal to 25, and we're feeling really good about ourselves, except that's a problem because we don't have a v, u and t equation that isn't a equals v take u over t. And we seem to find ourselves in the rather unenviable position of having an equation that has 2 unknowns. But the important thing here is to recognize what we mean by the force of gravity. Okay, when we say the force of gravity, that gravity, this is what most people say. What's gravity? Gravity's 10. Right? Do they really understand what that means? That means that the force of gravity is equal to 10 newtons for every kilogram, which sounds great, but we don't have a mass, so we can't get an acceleration that way. But if we have something that is doing 10 newtons for every kilogram, that means its acceleration is by definition equal to 10 meters per second squared. Okay, if that's the only force acting. Now I'm going to convince you of that. Let's say I have a 2 kilogram object. At 10 newtons for every kilogram, that's going to be 20 newtons. Right? So we pop that into F equals ma, or A equals F over m. So A equals 20 over 2. And as a result, A is equal to 10. And A is always going to equal 10 in this situation. For a 10 kilogram object, let's say 11 kilograms, just so we don't have a pile of tens. So for 11 kilograms, the mass is 11 kilograms, the force is 110, which is going to be 110 divided by 11. And again, that's going to give me an acceleration of 10. So in the very specific situation, and this is important, in the very specific situation where the only force acting on an object that's falling is its weight, it will fall with an acceleration equal to 10 meters per second squared. But that's not all. Because of the fact that these are vectors, we have the following situation, that our initial speed, I'm going to put this in red, was in the upwards direction. And our acceleration has to be in the direction of the force, which is in the downward direction. And because these are vectors, upwards and downwards matters. Now I've written u as 25, which is mathematically plus 25. So I've set upwards as positive. So my acceleration has to be negative 10 because it's in the opposite direction to that initial speed. Okay, it's backward. Now I could have done it the other way around. I could have said upwards was negative and I'd have minus 25 with an acceleration of 10. Everything would have been the same. Physics doesn't care which way you think up is, but it does care when one vector is traveling against another vector, and it does matter about your signs. So if two vectors are one's going upwards and one's going downwards, or one's going left and one's going right, one needs to be called positive and the other needs to be called negative. You know this already from when you're looking at forces. When you've got like 30 newtons to the right and 20 newtons to the left, then it's 30 take away 20. You've established right as positive, and then you take away 20 from the other side. Okay, so once we've got that, we finish our equation off with popping these in. So we get minus 10 equals v minus u, so that gives me 0 take away 25. Okay, it's take away positive 25 divided by our time, which we didn't know. That was what we were after, so that's over t. Alright, so we don't like the t on the bottom here, so we're going to multiply both sides of the equation by t, and that will give me minus 10t is equal to 0 take away 25. So minus 10t is equal to minus 25. Divide both sides by negative 10, and that gives you t equals 2.5. Now if you get this right, t will come out to be a positive number. If you hadn't put the negative 10 in there, you'd have got t equal to minus 2.5. A negative time, not a thing. Okay, I'm a big Doctor Who fan, but unfortunately traveling backwards in time is not a thing. Okay, so we shouldn't be seeing t equals minus anything here. Alright, now technically speaking, this is, because we've called this acceleration and this is negative, then it is not acceleration. Okay, a negative acceleration is a deceleration. Okay, and we are going to call that a retardation. Okay, because retardation means slowing. It's the French word en retard. I'm late. Okay, you've gone slowly. Right, so we've got a slowing down going on here, and that is right, because if I throw this up in the air at 25 meters per second, eventually it stops. It must be slowing down. It must be decelerating. Okay. Now, the more concerning one is when you're asked to calculate what is the deceleration. That seems to cause a little bit of dread amongst people. So let's have a look at that. So once again, let's take a little triangular object this time, so that we're not confusing it with the previous one. Let's fire it up into the air as before. So we're going to fire it upwards, and we're going to fire it up at a reasonable rate. Let's fire it up at 90 meters a second. Okay, and let's say at some time later, it's still going upwards and going upwards at 20 meters per second. Okay, so I'll put the wee arrow in. It's still going up. Right, and what we want to do, actually no, let's do better than that. Let's find out, let's say at some point later on it's got a time equal to 4 seconds later, 3 seconds later. Let's give it a speed. Let's give it a speed that suggests interesting things happening to it. Let's say it's got a speed of 30 meters a second a little bit later on. Okay, still in the upwards direction. And this time we're being asked to calculate the acceleration. Now notice I'm not suggesting to you that this object is flying freely up in the air. Okay, it could have a parachute attached to it, it could have some form of rocket boosters, it could have anything going on here. We haven't discounted air resistance, so we're not necessarily saying that A has to be 10 here. And I would make that clear in the question, you know, like I would call it a rocket with its engines firing, or a triangle that is subject to a massive amount of friction, or something along those lines. Calculate the acceleration. So on the face of it, this looks alright, that we have u equals 90, we have v equals 30, so it starts off at 90, and just stay chill. T equals 3 and a equals an unknown amount. And we're being asked to calculate the retardation of this object. Right, so A equals V take away U over T again. And we'll pop the T in, divided by T. Get myself a little equation. The only thing this package needs is a good equation writer, and then it would be beautiful. I wonder if the new version does. Anyway, so A equals V, which is 30, take away 90, and we should be panicking at this stage because 30 take away 90 is not going to be a lot of fun. Divided by 3. Alright, so A equals 30 take away 90 is going to be minus 60. So we get minus 60 divided by 3, which gives me then that A is equal to negative 20 meters per second squared. And what have you just found out? Well, what you found out is that this thing's changing at a rate of 20 meters per second every second. But even better, you've found out that that acceleration is in the opposite direction to my two speeds, because I've said that upwards is positive. Because I've got a negative, that's telling me my acceleration is directed downwards. So this is a deceleration. So my retardation is just equal to 20 meters per second squared. I get rid of the negative because what I'm saying here is I'm saying it's speeding up at a rate of 20 meters per second, it's speeding up at a rate of negative 20 meters a second every second, because acceleration is by definition that it's speeding up. Retardation though is by definition slowing down. So what I'm saying here is it's slowing down at a rate of 20 meters per second every second. Happy? Okay, I hope that's a little bit clearer for you, that when you get that. Now, the next question in this might be a couple of marks on tell me what this means. And because this number is larger than 10, okay, this is slowing down at a rate that's actually greater than what we would expect by just gravity. What you can say is that this thing is slowing down faster than you would expect. Okay, so it's possibly traveling through some very, very seriously thick objects. This may not be traveling through air. You may be trying to fire it up through water or something like that there. It's definitely encountering extra force that I could draw on this force diagram here, that there is definitely weight. There always is weight because it's acting, we said it was fired upwards, so weight will act downwards, but there's definitely another force in here. There's definitely another force pulling this backwards. Some form of drag force is pulling this backwards. Has to be. No choice in that matter. And I could extend this question. If I give you the mass, I could get you to work that out. Happy? Good. Good. Okay, with 7 minutes left, that took a bit longer than I expected. Let's take a look at the process of 6-mark questions. I was asked specifically to quickly run through nuclear fission. So let's do that in 6 marks. So the key to 6-mark questions is think, right, there's 5 or 6 points I need to hit here. And examiners have become very pleasantly recently, they've obviously gone to some form of charm school and have started giving bullet points for things that you need to include. Okay, so just answer what it asks you for. But anyway, for nuclear fission, the process of stimulated nuclear fission to get into a chain reaction, okay, the one that we're interested in, we need to know a few things. First of all, we need to know the name of the fuel. So it's uranium or plutonium. And first spelling mistake of the evening. Okay, uranium or plutonium, and we want to talk about nuclei here. Okay, we want to talk about nuclei. At no stage should you use the word atom. So uranium or plutonium nuclei, then they absorb a neutron. Okay, that's the bit that you do. You fire a neutron into one of them. Okay, this causes the heavy nucleus to split into 2 lighter nuclei. That's the definition of nuclear fission, with some mass converted to energy. Okay, there are also leftover neutrons, and that's why uranium and plutonium are so useful for this. Alright, so we want leftover neutrons to go on and run this cycle again, because then it runs back up here. There are leftover neutrons, and then other uranium and plutonium nuclei absorb a neutron, cause the heavy nucleus to split into 2 lighter nuclei with some mass converted into energy. Also some leftover neutrons, which then go on to get absorbed by uranium and plutonium. They absorb the neutron, cause the heavy nucleus to split into 2 lighter nuclei with some mass converted to energy. Also some leftover neutrons, which then go on to hit further uranium nuclei, and we could be here all day, and this is called a chain reaction. And that's nuclear fission in a nutshell for 6 marks. Of course, you've got a quality of written communication mark in there, so you want to pad that out a little bit. For nuclear fusion, on the other hand, which is the other one, we start with the name of the fuel again, which is deuterium. Oh, wrong color. So let me select the right color here. So we want deuterium and tritium. Okay, that is those are both isotopes of hydrogen. So that's hydrogen and hydrogen. This could be interesting. Trying to get the little numbers in. Let's get some small font. That's not going to happen. Okay, we want a 2 up there. So that's hydrogen 2 for deuterium. And so a mass number 2, this is an isotope of hydrogen, and a mass number of 3 for the tritium. Okay, they both have an atomic number of 1. Okay, so that's our fuel. Right. Then we have to force them together. So forced together. Oh dear, we're still in symbol. Change that. It's not liking that at all. Let's try that again, shall we? Though that is rather cool looking. Might leave that there. Select the right font. Okay, so what we want then is that we want these 2 light nuclei. And notice I'm saying light and heavy. I'm not saying big and small. Okay, 2 light nuclei forced together to form a heavier nucleus. So we go from multiple nuclei to single nucleus. Right. But that means some mass goes missing, so some mass is converted to energy. Just as before, and that's what makes it a nuclear process. That results, okay, so some mass is converted into energy, and that's the process here. That is the process. But what we want to, there's no chain reaction involved here, so we tend to talk about either doing the equations for it, or we talk about the difficulties with it. Okay, so where do we get these things from? We can get some of it from seawater, and we can get some of it bred from fission of lithium. Okay, which sounds interesting, but you know, it can be done. Okay, so seawater, and there should be an and in there because we don't breed seawater from lithium. So that's how we get our fuel. And then the problems, generally speaking, the problems with this, because we don't do this, and why we don't do this is that the pressure required is enormous, and like enormous is something of an understatement. Like the sun does this and has most of the mass of the solar system. Hello to those of you in chat that are looking for a shout out. Just glanced over there. And the other thing that we need is a temperature that is massive. Okay, we need a massive temperature, and both of those things put together make it very, 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 very difficult to do. But it is worthwhile doing because, and these are things that this was asked in the double award paper, that this gives 4 times the energy of fission, and 4 million times the energy of normal fossil fuel reactions. And I may be off the bottom of the page here with you guys, so let's just extend that downwards. Of normal fossil fuels. Okay, so I intended to get through like kind of a little bit more than that, but nuclear appears to be a big thing that worries people. But this is all you need to know. You need to know your fuels, you need to know the process is 2 light nuclei getting a heavier nucleus, and you need to know that this up here is fission, and this down here is fusion, and you need to be absolutely clear on the spelling. Normally physicists not particularly worried about the spelling, but the difference between fission and fusion we are exceptionally interested in. Okay, so no fusions. You know, people trying to go, I'm not sure what this is, so they write that in the hope that they're going to get something. That's immediately wrong. Okay. Fission out as well. Okay, has to be spelled correctly for you to get the things. That's what you get for leaving your steam running in the corner. Hopefully that's a little bit clearer. I'll take a quick check in chat. Anybody want anything done in 5 minutes? I'll wait a couple of seconds for the answer on that one. All the crosses, it's not that I particularly love these, it's in fact that I very much dislike these. These get immediately marked as XP for incorrect physics. X for wrong, P for physics. Okay, so they're not allowed. They're not allowed. Yeah, Steam notifications, time to play a bit of CSGO after this. Alright, everybody happy? Well, in that case then, all that remains to be said is make sure you get all of your revision in order. There is a bet on, for those of you who are following from other classes, I have a bet with my Triple Award class that if they all get A's, that there will be an evening of live streamed Counter-Strike Global Offensive on this channel with me at the massive level of Silver Elite, which is dreadful, getting shot repeatedly on stream for a few hours. Okay, but until then, revise hard, and always remember that physics rocks. It's true.